Okay, so let's get started. So, as you know, so I posted this lab assignment on Blackboard. And then, actually for this lab assignment, so you are requested to design single cycle processor, single cycle RISC-V processor. So actually, so you can design. So as we learned in the class, then so let's see the skeleton code. So like the other lab assignment, I provide the skeleton code of the single cycle RISC-V processor. Okay, so actually you need to complete this module. Okay, this module only. So actually, the single cycle processor includes the data path elements. So actually, we design the data path elements such as instruction memory, register file, ALU, and data memory. The fourth lab assignment. So you can use the what you design. So your design, or I also provide the complete design of these data path elements. Okay, so you can find the IMM.SV and then regofile.SV, ALU.SV, and DNAME.SV on the lab number 5 compression file, right? So we can use these data path elements. Okay, so you don't need to modify the actually this design module. So actually you need to complete only this single cycle CPU.SV. Okay, so I declare the required signals, required logic. Okay, in this single cycle CPU module. Okay, and then so you can find some variables. Okay, so actually because we have a complete data path element design. Okay, and then so actually what you need to do is connect some signals. Okay, and then okay, let's see this part. So actually so line number 155. So you can find the instantiation of a data path element. So it means that you have to use the submodule. So as you can see, you can find the module name here. IMEM. So this is the module name of instruction memory. Okay, and then actually these are parameters. Okay, so it's the parameters, and then these are input and output ports. Okay, so you can find the input and output ports here, and then you can find the parameters here. Okay, and then you can just connect some signals like the IMEM underbar address to the input port of the instruction memory. Also, you can connect some variables here. So what is this one? So output of instruction memory is instruction, right? So it is inst. Okay, you can find the inst here. Okay, inst here. So instructions is on output, and then so it's an instruction memory. So actually, you can just I just declared some signals or some variables for this single cycle processor, and then actually for instantiation, you can just connect the signals to the port of the data path element. Okay, so you can just declare the register file, ALU, and data memory like the instruction memory. Okay, and okay, so these are signals that should be used for designing a single cycle processor. So as we learned in the class, you can just connect the input and output ports of data path elements, right? And sometimes we require multiplexers, right? So we require multiplexers. For example, so for the input of ALU, so the second input of ALU can receive the output from register file or immediate value, right? So, but the multiplexer is not declared here. So you need to implement the multiplexers. Okay. So also you can so this is the main control unit part. So actually you can read the comments. So I kindly added the comments for this design. Okay. So this is the main control unit. And then what is OP code? So OP code is just some part of instruction. Okay? Actually, the instruction bit number 6 down to 0, right? So you can just define the OP code as using the instruction. Okay. So just read these comments. So actually, in the comments, I provide the required information for designing this single cycle processor. For example, the branch has the four-bit signal. Okay, so actually, in the class we learned about the branch signal, but it was 1-bit signal, right? It just detects BQ only, but in the this fifth lab assignment, our single cycle processor needs to support other branch instructions such as BNE, BLT, and BGE. So if you see if you read these commands, then you can find branch 0 this is the BQ. So which means that if an instruction is BQ, then branch 0 becomes 1, otherwise 0. Also, I define the branch 1, branch 2, and branch 3. Okay, here. And then also you can find the control signals here, right? So it's equivalent to the control signals we learned in the class. Okay, so those are output of main control unit. Okay, so then read, then write, and to read. Actually, name is the identical. Names are identical to the names of the output names of output signals of control unit. Okay, and then also we can define. We need to complete the ALU control unit. So it needs to generate the 4-bit ALU control signal, right? Oops. Here is the 4-bit ALU. Okay, the 4-bit ALU. So you can find the ALU control signal here. Okay, so you can just generate the ALU control signal. So actually learn. So actually, so I just provide how the ALU control signal is generated in the fourth lab assignment. You can just read the lab document for fourth lab assignment. And immediate generator. Okay, so we just define the immediate 32 and the immediate 32 branch. Okay. So firstly, we read the 12-bit immediate value from the instruction, right? And then we can generate the 2 different immediate 32. Okay. And then what is this? This is the program counter register. Okay. So it looks like this. So if you see the single cycle processor design, so you can find So this is the PC, okay? The PC, the program counter register, and then the clock is connected here. And then you can see that this is the PC underbar core. So this is the current PC, and then this is the PC underbar next. That's what we learned in the class. Okay. So as we learn, so actually this program counter part is this part implement the behavior of program counter. Okay. So we learn the PC next plus 4. What is this? It's PC plus 4, right? And then also, so we can get the two different program counter values for the next PC. So that can be PC next plus 4 and then PC next branch. And then I believe we can understand the name of these variables, right? PC plus 4 is a normal PC for the next instruction. And then PC next branch is the target of a branch instruction. And then multiplexers. So you need to implement the multiplexers because I did not include the multiplexer modules. But we can easily implement the multiplex. Okay, so you can see chapter 4 document. Lecture slide. Also, ALU input and then register file input, and then these are input signals for instruction memory, register file, and data memory. Okay. So actually, you can just define the appropriate bit signals. For example, IMEM address. Okay, so actually PC is connected to the IMEM, okay, IMEM address port. But if you see the IMEM, the instruction memory, then when the address is incremented by 1, then the actual address 1 assigned 4 bytes, right? So you need to consider this part, okay? Because the PC is the real address in this file, okay? So it's the byte address, but in the instruction memory, the address 1 assigned 4 bytes of data, okay? So you need to consider this. Okay, that's it. So based on the one you learned in the class, you need to complete this single cycle process design. But it will be very helpful if you can complete this module, this single cycle process module by yourself, and it will be very helpful for you to understand the real design, and then how the wires and then how some data has elements are connected to each other. Okay. Any question? So actually the lab document is very simple. So this is the test code. Actually, so if you see the compression, so contents of the compression file, so you can find the contents of instruction memory. Actually, the instruction memory includes these assembly codes. Okay. So if you run the test bench, then the single cycle processor will read instructions from this instruction memory, and then the single cycle processor will execute these instructions. Okay. So actually, the description is very simple. The lab document. Any question? Okay. I hope everyone can complete this single cycle processor design. And then before starting today's class, I will briefly introduce about some simulation tools for RISC-V. Okay, so these are computer architecture tools, and then we can use these simulation tools for computer architecture research. Also, the simulation tools can help you understand the detailed behavior of the processor. Okay. So actually, we are learning about the hardware system of computer systems, right? But as you can see, the hardware systems are very complex systems, right? So these are some examples. So we can use the real hardware for our research. So actually, I use this board, this development board. So actually, so we can use the real systems for this computer system or computer architecture research. But you know, it's very difficult. It's very difficult to modify the inside of this process. Actually, it's not possible. We cannot modify the inside of processors because these are chips, the solid state chips. Okay, so it's a semiconductor devices. Actually, these are stored. Okay, we cannot modify. So also we can use real systems, and then real systems can run system softwares or operating systems, and also these systems can also include the FPGA. So actually, we can modify the logic design inside of FPGA, but it's also very difficult. So for architecture research, we can use simulators. Then what are simulators? So this is the definition of architecture simulators. The architecture simulators emulate. So emulate means that it's just mobile. Okay. So we can use the meaning for this emulation, but so actually it represents mobile in Korean. Okay. So emulate the operation of computer processors or systems, but it's software. So architecture simulators emulate the behavior of computer system hardware, like processors or real hardware systems using software. Okay, so what is the benefit of software? We can easily modify the software, and then actually we can include our ideas on software, and we can just test. Well, we can just evaluate our ideas using these simulators. Okay. So RISC-V also provides actually not the RISC-V. So some researchers provide the RISC-V simulators. The first part of simulator is the assembly simulator. But actually, in the first and the second lab assignment, I also introduced the instruction simulator, right? It's called Spike. So actually, assembly simulator is also works. It also emulates some execution of assembly instructions like the Spike. So it executes the RISC-V assembly instructions. So as I mentioned, we cannot execute RISC-V instructions using our smartphones or using our laptops because the ISA is different. Because the ISA is different, these processors, such as the Intel CPUs or ARM CPUs, cannot understand RISC-V instructions. So it cannot be executed using our hardware. So, but using the assembly simulator, it's software, so we can execute the RISC-V instructions. And then, as I mentioned, the spike, it's RISC-V ISA simulator. Spike is also a kind of assembly simulator. Okay. So actually, we did this part. So we use the cross compiler. And then we install the RISC-V cross compiler, and then we can generate the RISC-V binary code from the high-level language code. And then using the assembly simulator, we can execute the compiled binary code. Or we can use the Cameo. So Cameo is the virtualization tools such as VirtualBox or it's a VMware, okay? But Cameo is a little bit different because so Cameo can execute the different ISA platforms. So actually, even though you install the VirtualBox on your x86 computers, but you cannot execute RISC-V binaries because ISA is different. But if we use Cameo, it's a software virtualization tool. So then we can execute RISC-V instructions. We can execute the RISC-V binary code. Okay. So actually, there are many assembly simulators here. And then again, so Jupyter is part of an example of RISC-V assembly simulator. So as you can see, so we can execute the RISC-V instructions here. So you can find some potential registers. Okay, here. But I want to introduce the graphical architecture simulator. Okay, so we are very familiar with the graphical tool, and then it's also very convenient. If we can use the graphical tool, so we can easily understand the behavior of this processor architecture. So I think this is a very great tool. So it's a very great tool. Okay. So you can so this is the right RISC-V simulator. Then you can download the RIPes on this GitHub repository. And then I believe you can execute the RIPes on your Windows computers or Mac computers. Okay. So this is the example. I will show the example. Here's the it's right. Okay. So this is the right RISC-V tool, and then so actually you can what is this? This is the single cycle RISC-V processor. So as you can see, you can find the title of processor here, and then if you click where is the processor here? Okay, not this one. You can click this icon, so very small. Then we can select also very small. Actually, so we can select the single cycle processor, and then it's a 5-stage processor without coding or hazard detection. Blah blah blah. 5-stage processor, and then 6-stage dual-ish processor. So we can select some different architectures, different processor architectures. So we learned about the coding unit and the hazard detection unit in the previous class. So I will select the 5-stage processor. Okay. So you can find the very familiar figure, right? It's very similar to the 5-stage processor architecture we learned in the class, but it's a little bit different. Okay. So this structure fetch, structure decoding, execution, memory write back. Okay, and also you can find the pipeline registers here. Okay, so, and then so you can find some architecture figures in this right simulator, and then also good thing is that we can execute this 5 instructions, and then this simulator shows the instruction flows vertically. Okay, are you sure? So I think here's the file. You can load example file here, assembly. Oops. File assembly. This is just the example. So the factorial as the assembly code. So you can find this assembly code here. Okay, so this is the code in the instruction memory, and then this is the assembly code. So this is the compiled instructions. And then processor part. So you can find the first instruction here. So first instruction is in the instruction fetch stage, and then if you click no, this one. Okay, so if you click this icon, okay, you can find that the new instruction is fetched, and then here's the AUIPC. AUIPC is the instruction decoding stage. Then click. So you can see where the instructions are in the 5-stage pipeline architecture. Okay. So we can actually, so we will learn about the control hazard and the stress, but you can find that so because of the control hazard by branch instruction, pipelines are flushed. So it means that these pipeline stages are filled with the no instruction. Okay, it's flushed by because of a branch instruction. Okay, so actually we can find some behavioral instructions in the real 5-stage pipeline process. Okay, very good tool. And here. So we can find BGE. So we can observe some pipeline flushes by BGE instruction. Also, so we can observe the contents of register files here. And then if you just click the instruction part, and so we can see where instructions are in the 5-stage processor. So you can find that this instruction is in the instruction fetch stage, and then actually 2 instructions are flushed. And then this instruction is in the memory, and then this instruction is in the write back stage. Right. So I hope. So sometimes it's a little bit tricky to understand the behavior, the detailed behavior of 5-stage pipeline architecture. But using this graphical tool, we can understand. We can understand where instructions are in this 5-stage pipeline processor. Okay, so I think it's a great tool for studying computer architecture, and then I hope everyone can understand the detail, the behavior, the real behavior of this pipeline processor. Okay, so it is because what is so as you can expect, the next lab assignment is to design pipeline processor. That it actually the designing pipeline processor is more difficult than the design of a single cycle processor. So it is because so we need to consider the hazard detection and then data forwarding. So and then this is the difficult part in the pipeline architecture. So actually the basic concept, the baseline concept of pipelining is very simple. And I believe everyone can understand the baseline concept of pipelining, but because of hazard, then because of hazard, the design is the more difficult. Okay. So this is I introduced the RISC-V simulation tool here, and then you can use this tool for understanding the pipeline processor architecture. Okay. So, what? No. So I will distribute some papers for updates. Then so the quiz questions are very simple, and then also you can see the lecture slide. Okay, this is open book quiz, so no problem, right? Everyone has paper? Okay, collect the first spectral. I collect the paper. So what is this one? What is the answer of this one? So add instruction is executed. So instruction needs to be set from instruction memory. So instruction memory is accessed, and then add instruction like the add x1, x2, x3. So add instruction reads out from register file. So register file is also accessed. And then ALU is accessed, but data memory is not used, right? So add requires instruction memory, register file, and ALU accessed. And then this is very important. So you need to memorize. So write the three kinds of hazards: structure hazard, data hazard, and control hazard. Okay. Then what kind of hazards can be observed if the processor has one united memory? So which means that the single cycle processor, so in the pipeline, processor has one instruction and data memory. Okay, so which means actually in the single cycle processor architecture, we learned that this processor has separated instruction and data memory, but if the processor has one united memory, which means the instruction and data memory is merged. So what kind of hazard? Each instruction, right? So memory instructions. So the memory instructions, the load instruction and store instruction is to access memory, and then but every instruction also accesses memory. Okay, so but the load instruction also needs to load or store instructions also need to access the memory. So actually the memory port is already occupied the instruction, but the load instruction also needs to use this memory ports. So because of the lack of hardware resources, the clock cycles are wasted. This is the structure hazard. Okay. Very simple. Here is the this one. This one. Okay. So okay, so in the previous lecture, we learned about the hazard detection unit. So it means that how to handle hazard or data hazards using in the pipeline processor. So I mentioned that. So actually, when we learned about the data hazard, so I explained that we can avoid data hazard using data forwarding. But if the formal instruction is load instruction, so we cannot, and then the very next instruction requires the data from the load instruction, and we cannot avoid the data hazard. So in this case, then the pipeline store needs to be stored. Okay. So actually, these behavior needs to be implemented in the pipeline process. That's what I explained in the lecture. Okay. So this is very important part actually, and then also it's a little bit tricky. So as I explained, the baseline concept of pipelining is very simple, but implementing this data forwarding or the pipeline stores it's a little bit tricky. It is a little bit difficult. Okay, so it's a very important part. So please watch the lecture video. Okay. Then as you can see, the condition, this. So we need to also generate the control signal for this data for unit and then hazard detection unit. Then actually the condition is also a little bit complex. Okay, so we need to consider the also corner cases. Okay. And then how to store the pipeline? So the instruction is stored when the instruction is in the ID stage, right? Because if you watch the video, so you can remember this figure, okay? So when the add instruction is in the ID stage and then load instruction is in the execution stage, then the normal case, the add instruction, the next cycle, the add instruction will be in the DX and then load instruction will be in the memory. But if the add instruction, so data dependency, if the data dependency is observed, so which means that if the add instruction use the data from load instruction, then add instruction cannot use the data from load instruction if the add instruction is in the EX stage, right? So only the load instruction is propagated to the ME stage, the memory stage, and then add instruction is in ID stage. So this is called pipeline stores. Okay, pipelining store or pipeline store. So, which means that we need to we need to add the no operation, right? So it's called a bubble, and then add instruction stays in ID stage. And then obviously the following instruction. The instruction in instruction fetch stage also stored. Okay, because this is pipeline. So we need to implement this bubble generation. Okay, so and then the instructions in instruction fetch and ID stages need to be stored. So this behavior needs to be implemented. Okay, so it's what I explained here. So in order to generate the NOP operation, NOP, then we can just make all control signals 0. Okay, and then we can just block the propagation of instructions in instruction fetch and ID stage. Okay. But if the pipeline stores are observed, performance is irrelated, right? Because the clock cycles are wasted using bubble, so no operation. Okay, actually, the instructions cannot be executed for this clock. So we need to avoid this case, the pipeline stores, for improving the performance of processor. Then I already explained about the code scheduling. Then, so here. And so now, so I will explain about the control hazard. So what is the control hazard? So you need to explain. Okay. So clock cycles are wasted because of control instructions. Okay, and the control instructions include branch instructions, jump instructions, and exception handling. Okay, so it's control hazard. Control hazard is the hazard. So I mentioned that hazard are events that waste clock cycles, and then control means that clock cycles are wasted by control instructions, and control instructions include branch, jump, and exceptions. Okay. Okay. So why and why? Why clock cycles are wasted when these instructions are executed? So actually, the common behavior of these instructions is it updates PC with the target of branch, jump, and exceptions. Okay, it's a target. So actually, when instructions are executed in the processor, we just increase the PC. So actually, we just increase the PC by 4. Okay. So if there are no branch instructions, jump instructions, or exceptions, then the PC values is just incremented by 4 every clock. Okay. And then we can read the next instruction, and then we can just execute the next instruction without wasting clock cycles. Then why branch instruction or jump instruction and are executed? And then actually I mentioned that actually when these instructions update PC with the target of these instructions, and clock cycles are wasted. Okay, then why? It is because the target of these instructions like branch, jump, and exception, target of these instructions is updated late. Okay. So what does that mean? So actually the instruction is fetched in the instruction fetch stage, right? And then we just we can in order to fetch next instruction, then we can just update the PC as the PC plus 4, right? Then when the branch instruction is executed, we can know the result of branch instructions in EX stage. Right, because the branch instruction is executed in Q, X1, X2, and target. So actually we can know the target of branch instructions in the ID or EX stage. Okay, it depends on the hardware implementation, but actually in order to compare these two values, and the values in x1 and x2, then the processor uses ALU, right? So ALU is used, so we can get this comparison result in EX stage. Okay, but in order to update the program counter immediately, then we need to know the next PC, the instruction fetch stage. So because we can know the result of branch instructions late, and if the branch instruction is true, then it means that it's taken. If the condition of branch is true, then it is called a branch is taken, and we need to cancel the fetched instruction. So in this example, the BQ is the condition of a branch instruction is rejected. So we can know the result of branch instructions in EX stage, and then the PC next. So next PC is determined. The PC next stage is determined in ME stage. Then when the branch is in the write back stage, then the next PC is updated. Okay, so this is just the example. Okay, then what's the problem? Before the PC is updated by the target of the branch instruction. So actually, I mentioned that when the branch instruction is in the write back stage, then we can the current PC becomes the target of the branch instruction. So which means that this target of branch is fetched. Okay, here. Problem is that the branch is here in the write back stage, and then the target instructions by branch is in the instruction fetch stage. And how about this one? Actually, these pipeline stages, so these pipeline stages, such as memory stage, execution stage, and ID stage, includes wrong instruction. Okay, because this is the correct instruction. Because the branch is taken, but the processor thinks that the branch is not taken. So actually the processor fetches the very next instruction and next instruction, because the processor does not know the condition of a branch instruction. But when the PC is updated by the target of a branch instruction, here this is the correct instruction, then these instructions are incorrect instructions. So which means the processor needs to cancel these instructions. Okay, you understand? So why cycles are wasted? Because the processor can know the result of a branch instructions late. Okay, but the processor just fetches the next instruction, even though the processor does not know the target of a branch instruction. Okay, so actually the result of a branch instruction. So the fetched, and next, but when the branch is taken, then the new instruction, the correct instruction is to fetched. So these instructions need to be cancelled, which is flushed. Okay, do you understand? So if you see the right, okay, I will show again. There's the okay. So so actually the the architecture is a little bit different. So you need to consider the different architecture here. So as you can see, the branch instruction is in the instruction fetch stage, right? And then also you can find that other instructions occupy pipeline stages. Okay. In the next cycle, the branch is here, but we don't know. Even though a branch is in the ID stage, can you see the control here? Okay, the branch is here, the ID stage, right? But as you can see, the next instruction, the PC plus 4. The next instruction by PC plus 4 is fetched. We don't know. We don't know that this branch is taken or not taken. So which means we don't know the condition of branch instruction. Okay? Because the branch is in the ID stage. The next cycle, branch is in the EX stage. Then we don't know. So this process just gets the next instruction here. So add I is in the ID. So another add I is in the instruction fetch stage. But in this processor, the branch detection unit is the EX stage. So then we assume that in the next cycle, the correct target can be fetched. Okay. So there is a dedicated branch unit here. Okay. So this architecture is a little bit different. So what will happen? Branch is taken. So correct instruction is fetched in the instruction fetch stage. But as I mentioned, these instruction in ID and instructions in instruction fetch stage, these instructions are incorrect instructions. So those instructions need to be flushed. So flush means in the toilet. The flush means that water is flushed down. Okay. So flush means that the instructions are cancelled. So the branch is in the ME state because in this architecture, the branch is determined by this branch unit. Then the branch is in ME stage, and we can fetch correct instruction, target of branch. But these instructions need to be flushed, cancelled. You can find the flush here. Then how many cycles are wasted? 2 instructions are cancelled. So which means 2 cycles are wasted. Okay. So when the branch is taken, then in this architecture, the 2 cycles are wasted. Okay. And then, okay, let's go back to the slide. But in this example, so as I mentioned, the architecture is different. So in this example, when the branch is in the write back stage, then we can fetch correct instruction, the instruction fetch. So these instructions so these 3 instructions need to be flushed. So 3 cycles are wasted. Okay. So this is the control hazard. So cycles are wasted because of branch instruction. Okay, do you understand? So then how can we reduce the control hazard? So what's the problem? So when I explained about the control hazard, so what is the problem? The main problem is that branch is, we can know the branch is result late, which means that we can know the result of a branch instructions late. Then how can we reduce control hazard. So if you can know the result of branch instructions earlier, then we can reduce control hazard, right? Obviously, right? So, and then in order to know, so actually, let's think of BQ, X1, X2, and immediate. So, and then if the branch is taken, then branch is the PC is updated by PC plus immediate. So, in order to know the result of a branch instruction, then firstly, we need to compare X1 and X2, and then we need to know the result of this comparison, and we need to calculate the PC plus immediate. Okay, this is the target of the branch instruction. So, so in order to execute branch instruction, we need to know the target of the branch instruction, the PC plus immediate, and then we need to know the result of comparison. Okay. The problem is that in this architecture, then actually this X1 is compared with the X2 by ALU in EX stage. Okay, but in order to support the BQ just compare the X1 equality of X1 and X2, the two source resistors. So this comparison is actually very simple. We don't need to use subtractor, okay? Because we just check the equality of these two data, X1 and X2. So actually for this comparison, in order to check the equality of two data, we can use the exclusive OR gate. Why? Because the exclusive OR gate is a two input A, B, and Y is the output 0, 0, 0, 1, 1, 0, 1, 1. Then the result of exclusive 0, 0 exclusive OR is 0, so 1, 1, 0. Right. So for the exclusive OR gate, if the two inputs are different, then output is 1. Okay. So actually for the 32-bit data, so we can use the bit by bit, the bitwise exclusive OR gate. Then if we use the very large OR gate, so if 1 is detected, then it means that, oh, this is different. So what I want to say is that equality check is implemented using simpler hardware. And then, if we use simpler hardware, then delay is also short. So we can include this delay in the clock period inside of it. So even though this short delay is included, then we can make the sum of the delay is less than sum of the delay is less than clock period. Okay. So the idea is that, so actually this part is so immediate is included in the instruction. Okay, and then this is the add operation. Actually, so we can know the PC. We can know the PC value in the ID stage. Also, we can know the immediate value in the ID stage, and then PC plus immediate is also kind of a simple operation. Okay, so which means that in the ID stage we can get the PC plus immediate. Okay, if we can use the add-on here. So as you can see, what is added? In order to reduce the delay of branch instruction, actually the delay of queue, because so we assume that our processor just supports the EQ only for the branch instruction. So in order to reduce the delay of branch instruction, then we can add the equality check unit here, okay, here, and then immediate plus PC can be calculated in ID stage. Okay, so we can get the condition of branch instruction here, the condition, and then we can get the, this is the target of the branch instruction. So what's the benefit? So we can know the result of a branch instruction in the ID stage. Okay, then the PC next is determined in the ID stage. And then next cycle, the branch instruction is in the EX stage, then we can fetch correct instruction, the target of a branch. So in this case, only one cycle is wasted. So as you can see, you can observe bubble here. Okay, so by reducing the delay of branch instruction, we can reduce the control hazard. So this is obvious, right? So I explained that because the result of a branch instruction is resolved late. So we can observe many cycles wasted, many wasted cycles. Then if we just reduce this delay of branch instruction, then we can reduce control hazard. Okay, this is the possible technique, but actually, this is not a good design. But so because this design causes new hazard. So actually, I like the design in RISC. So branches are determined in each stage by dedicated branching. Okay, so I like this design better because so you know BQ reads X1 and X2. So BQ reads two source registers from register 5, and then it is checked in the ID stage. The problem is that X1 and X2 can be the result of add instruction. What's the problem? The problem is that this processor has data coding box in the EX stage. Actually, I explained that if the formal instruction is add instruction, like add X1, X2, and X3, then we can reserve, so we can avoid data hazard using data coding. Okay? So if the next instruction is also another archive instruction, like the X4, X1, and here, then it's possible, so it's okay. But problem is if the next instruction is the BQ branch instruction, like X1, X4, and immediate. Problem is this branch instruction needs to receive data by add instruction. But in this design, forwarding mux is here. Okay, what's the problem? Because the forwarding mux is here, then the result of add instruction can be forwarded to the next stage when the add instruction is in the memory stage. You understand? But the branch instruction is reserved in ID stage before data forwarding multiplexers. Okay, so which means that the result of add instruction cannot be forwarded in this case. Okay, so actually this design creates new data hazard. So that's why this design is very complex. So I don't like this design. But in the textbook you can find this issue. Okay. So it means that the formal instruction is any instructions like add instruction, one load instruction, and then the following instruction is a BQ, then it causes data hazard. And then this data hazard cannot be resolved by data forwarding. Okay, so in this case, the branch needs to be stay in ID stage when the result of add instruction until the add is in the write back stage. So the result of add instruction is delivered to the register file, and then this data is internally forwarded in the register file. So actually, 2 cycles are wasted by this kind of data hazard. Okay, so this is the problem. So actually, this is not a good design. But if we in the right, so need to share. Okay. So I can use that. Okay. So actually, I copied this design. This is the design. So in the 5-stage pipeline processor by write simulator. So actually, we can find that the branch is here because this is just comparison. Okay, so and then if you see that this branch received the 2 data after the, what is this one? This is the data forwarding boxes. Okay. So these are data forwarding boxes, and then branch instruction is located after the data forwarding multiplexers. So which means that in this case, if the formal instruction is the add instruction, then the next instruction is the BQ, then the result of add instruction can be forwarded. Okay, because the branch is located after the forwarding multiplexers. So using the existing forwarding unit, then we can resolve the data hazard by any instructions and branch instruction. Okay. So, but in this case, if the branch is taken, the control hazard is equivalent to 2 cycles because the branch is in the any, then we can fetch new correct instruction. The branch is not taken, so no penalty. It's the same actually. Okay. So that's why I don't like this design. So actually for our lab assignment, we will implement this design. Okay. But the design by principle. Okay. Okay, so I'll stop here and then actually, so this cultural hazard are also kind of very important topic. So I hope everyone can understand the cultural hazard. Any questions? 감사합니다.